All right, let's start talking about the Sylow theorems. So these are really important, and I've heard these described as sort of the among the last results that you can say for a very large class of groups. Once you get beyond Sylow theorems, a lot of the stuff you do in group theory gets to really more specific cases. But yeah, well, I guess this isn't. Is this? Yeah, it's just finite groups. So whatever. So definition. Okay, so let the order of G. Well, obviously G is a group, but it's going to be N, which is P to the R M, where P is prime and P does not divide M. Okay, then a subgroup, capital P and G, such that the size of P is equal to P to the R, is a Sylow p-subgroup. Some people will put this p dash in the front here and call it a p-Sylow subgroup, but this is sort of nice because previously we defined a p group and we had the p dash group, and so here is the same thing, but then just the Sylow is sort of like an sylow thing. Because, of course, P to the R is a P group. It just happens to also be a Sylow P group because of the fact that it's contained in a group of size P to the R M where P does not divide M. So, anyway, oh, and by the way, I'm going to try an interesting thing for these Sylow theorem videos over here where I'm actually going to state them all here and then prove them all here. So that's why I'm not using this board yet. So anyways, let's look at some examples. Let G equal S4. Then the size of G is 4 factorial, which is 2 cubed times 3. All right, so here we're going to let n be 2 cubed times 3, and then p is going to be 2, r is going to be 3, m is going to be 3. So 2 is the p that we're going to be looking at here. So I'll just write that. Let p equal 2, but I'm not going to write the other things because you can just figure that out from there. Okay, so let n be the identity and also everything of the form A, B, C, D, where A, B, C, D are disjoint in S4, excuse me, where these are disjoint indices from 1 to 4. Wow, I really saved a lot of time using that ellipses there. But anyway, so we have 1, 2, 3, 4, 1, 3, 2, 4, and then 1, 4, 3, 2. So those are going to be, so there's only going to be 3 things here, and this is 1. So then we have n equals 4, and you can also prove that n is a subgroup of S4. Okay, so let's see here. Since the order of n is 4, that's 2 squared, which is not 2 cubed, and therefore n is not a Sylow 2 subgroup of S4. However, you can figure out, you can do the work here, but if you look at the subgroup generated by n and just the element 1, 2, 3, 4, then basically what you're going to do is you're going to associate with every element of n, you're going to get another element from here. And so this is going to be 8. So this is a 2 Sylow subgroup. Obviously, as soon as we know that n is a subgroup, we know that this is a subgroup. All you need to check is that the size of this equals 8. And of course, I'll leave that to you if you're interested in it. I'm sort of not. This is just an example that doesn't have really any emotional meaning for me. This is just so that, oh, hey, this would be an example of a Sylow subgroup, and here's an example of something that is not. So this is a 2 Sylow subgroup of S4. All right, and so now we can state the Sylow theorems. And of course, there are there's a whole bunch of numbering systems for these. But we're going to adopt this one. So Sylow p-subgroups exist. I.e., if you have a group G of size p to the rm, where p does not divide m, and blah, 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 then you always have a subgroup of size p to the r. Okay, so that's the first one. Next, let H be a subgroup of G, be a p-group. So H has size p to the s for some s less than or equal to r. Then there is a Sylow p-subgroup P in G such that H is contained in P. So every P group is contained in a Sylow p-subgroup. Also, if P and Q are p-Sylow subgroups, just for consistency, let's see here, I think sometimes people say p-Sylow subgroups, sometimes people say Sylow p-subgroups. I'm going to try to be consistent. So if P and Q are Sylow p-subgroups, then there is some G in G such that GPG inverse equals Q. Or in other words, all Sylow p subgroups of G are conjugate. And that actually turns out to be really important. Let's see here. If NP is the number... Oh, by the way, one thing real quick here. So we really have two statements here. They're sort of related, but I don't know, I guess we just combine them into one. Anyways, if NP is the number of Sylow p subgroups of G, then we have two really useful facts. NP is going to be equivalent to 1 mod P, and the other thing is that NP is going to divide M. And that last one is really useful, especially because in a lot of problems you're going to be asked, let's say, like you'll be given some group of some size and be asked, okay, how many Sylow 2 subgroups do you have? Or how many Sylow p subgroups do you have for some given p that divides the order of the group? And sometimes just these two facts alone give you enough information to be able to figure out what NP has to be. That won't always be the case, but in a lot of problems there'll be enough. In most problems they'll give you at least some useful information that you can at least narrow it down to a few things and then consider, okay, well, if NP has to be either this or this, then you can consider like a case-by-case basis and figure out whatever you want from there. All right, so we need to prove these three things, and it looks like I have enough time to prove the first one. So proof of A, Sylow p-subgroups exist. Okay, so we're actually going to use what we did in the last video here. So we're going to let script E be the collection of subsets of G of size P the R. That is not what I want to write there. I want P to the R. Then G acts on script E by, ooh, I'm getting better at drawing those. That looks really nice. I'm going to have to never erase this ever because I'm never going to draw one that nice again. So anyways, G applied to Y1 through YPR is going to be equal to GY1 through GYPR. And of course, as we talked about last time, this is a group action. Okay? And remember, Y here does not need to be a subgroup. It's just a set. See here. Then, there must be some element X in script E such that the orbit is not divisible by P because otherwise we would have what? We'd have the size of script E would be equal to, remember, this is the size of N choose P the R, which is the sum overall alpha in G in the collection of orbits under this action of G times X alpha. And so if it's not the case that there is something that's not divisible by P, then all of these are divisible by P. And so every element here is divisible by P, which means that this sum is equivalent to 0 mod P, which contradicts that lemma we proved last time, which is that, what did we prove last time? We proved N choose P the R is equivalent to M mod P? M, right. M mod P. Remember, that was that really sort of neat lemma that we proved there. Okay. Okay. So we've chosen X in script E. So next, we're going to let Hx be the stabilizer in G of this element X. And of course, this is a subgroup of G. Then I claim, what do I claim? I've left a cliffhanger here, but basically I'm claiming that this gives us what we want. So it's a subgroup, and we want to find a p-Sylow subgroup, so I claim it's a p-Sylow subgroup, i.e. I claim that the size of Hx is equal to P to the R. Okay? So how do we prove that? Well, we first use the orbit stabilizer theorem. We know that the orbit of X under G is going to be equal to the size of G divided by the stabilizer, which is H sub x. And this is not equivalent to 0 mod P because we chose G dot x to not be divisible by P. So since this is not divisible by P, this is not equivalent to 0 mod P, and so this is not equivalent to 0 mod P. So since that's true, we have that hx, well, let's see here. G is m times p to the r. So there are r factors of p here. And so if hx doesn't cancel out all of those, then there's going to be some p left over in the prime factorization of the size of this quotient. And if there's any p left over, then this is equivalent to 0 mod p. And that can't happen. And so hx needs to cancel out every single p. And how many of them do we have? R many. And so hx must divide p to the r, because that's the only way that we can guarantee that it will cancel out all of those factors. Okay, so we have that. So that's good. No, that's not what I meant to write. I meant to write this backwards. We need p to the r to divide the order of hx. Because, i.e., we need hx to be, the size of hx needs to be p to the r times possibly something else. Because it needs that p to the r to cancel out the p to the r's in G, and it needs, well, it doesn't need to have something else, but it could. We don't know yet. But now we're going to prove that it doesn't have something else. Also, given some, let's say, x naught in capital X, I guess we could just call it little x, but then, like, it's hard to see, well, if I write x, maybe I wrote a lowercase x really big or an uppercase x really small, and you don't know. So I'll just call it x naught so that you know it's lowercase, just in case it's confusing in any case. So, yeah, and we can do this because x is just a subset of G, so we could just do that. It's going to have some element. So we have this x naught. Define a map f, and we're going to go from hx into x by f of x is going to, nope. Let's see here, we're in hx, so we're going to call it lowercase h. F of h is equal to, wait, did I say x naught is in x? Right, x naught is in x. Yeah, okay, sure, it all works. This is going to be h times x naught. F is injective because if we have f of h equals, suppose f of h equals f of h prime, then we sort of do the obvious thing from here. This means that h x naught equals h prime x naught. Okay. So, but x naught is an element of the group because it's an element of x, and x is an element of squiggly e, and so that's a collection of subsets of G, and so it is an element of a group. And so rather in the last case we just had x had just our script e being subsets of some set. Here there are subsets of a group, and so x naught is guaranteed to be in a group. Yeah, so this is x subset of G. Not a subgroup of G, but a subset of G. So anyways, so what we can do there is we know that x naught has an inverse, and so we can just multiply by that inverse. Just cancellation. And so then we get h equals h prime. Okay, and that's exactly what you need to prove if you want to prove that a map is injective. And so f is injective. Thus, if we have an injective map from this finite set to this finite set, then that means that the size of hx needs to be less than or equal to the size of x. But what's the size of x? X is an element of script E, so it's p to the r. So if hx is an element, is a subgroup of size p to the r, of size less than or equal to p to the r, which divides p to the r, then we have the only possible outcome is that the size of h to the x is exactly p to the r. Okay? So hence, G has a Sylow, not a p-Sylow subgroup. I think I learned that at some point, but now I'm trying to break that habit. A Sylow p subgroup. Okay? And there we go. That's our proof of this result.